Okay, morning guys. Let's continue with where we stopped off in our last class regarding the border plot. So, if you do a small recap, this was the example that we were working with. This was the example that we were working with, and we did two steps. The first one was the normalization. So, we've done the normalization part, and then secondly, how to complete the description. So, that's the two parts that we've done, right? Now, the step that we're going to be doing today is the magnitude slope contribution, right? Slope contribution. So, where does this come from? Remember when we talked about the border plot, we said that it's a curve, right? So obviously these terms that we have put in our description, that is this pole at 0, pole at -1, pole at -2, all these need to be combined together to create a slope. So how do we determine the slope? That is what we're going to be asking ourselves today. So to answer that question, we have this very simple table that I've created. Now this is called the magnitude slope slope contribution, and you can see here poles, zeros, first order terms, second order terms. So a pole, if it is first order, it breaks at -20 decibels per decade. A zero, if it is first order, breaks at +20 decibels per decade. Now, if it's a pole which is second order, then it breaks at -40, that is twice the first order. And if it's a zero, it is +40 decibels per decade. Okay. Now, if it's a third order, it will be 3 times. So it is -60 and +60. If it's a fourth order, it will be -80 and +80. So for our terms and purposes, we will only be looking at first and second order. So this is how it's going to break. So this is the contribution that a pole term or a zero term will bring, right? But now before we do that, we need to determine or expand on something that we did in our last class, that is the break frequency, right? So let's determine what are the break frequencies here. Okay, now the break frequency for the pole at 0, right, it is 0 radians per second. For the pole at -1, it is 1 radians per second. For the pole at -2, it is 2 radians per second. And the 0 at -3, it is 3 radians per second. So we're going to put that over here. But we have a problem, right? We can't work with 0 radians per second. That is something that we cannot do. So what we're going to do is we're going to put a value very close to 0. Let's put it as 0,1 radians per second. Okay? The remaining, it's fine. It's 1 radians per second. 1 radians per second, 2 radians per second, and over here it's 3 radians per second. Now we bring in that slope contribution that we discussed here, right? So let's just take a snapshot of this one and let's bring it over here so that it makes our work a bit easy. Right, there we go. Now with this we can now start working on our slope, right? So what is the rules? So if you have a look at the rules here, you'll see that the break frequencies for the magnitude pole, each term will break at its break frequency. Okay, the break frequency is determined by the location of the pole or the zero term. We already determined that. The pole at 0 or origin has no break frequency, but for calculation purposes we take it as 0.1 radians per second. So we mentioned the first 3 points. The next point is each term only starts braking at its brake frequency and continues till the very end. So keeping this in mind, let's start work on this one now. Right, so the pole at 0, right? So the pole at 0, we know that it will start braking at 0.1 radians per second because that is what is assigned to it, right? Now, what will be the slope contribution? It will be minus 20 decibels per decade because it's a pole term, right? So we're going to put it as minus 20, and it's going to continue. Remember what this said. Each term only starts braking at its brake frequency and continues till the end. So it will be minus 20, minus 20, minus 20, all the way towards the end. Let's look at the next term. The next term is the pole at 1 radians per second. If we go back to the rules, it says that each term brakes at its brake frequency, right? So if you come back here, for the pole at minus 1, the brake frequency is 1 radians per second. So effectively it means that nothing happens to it at 0,1 radians per second. But at 1 radians per second, it starts braking. And what is the brake? It will be minus 20 because it is a first order pole term, right? Where do you get it as a first order pole term? If you go right back up to where we did it, where did this pole at minus 1 come? It came from S plus 1, and S plus 1 is a first order term. So it's minus 20, minus 20, minus 20, and this is because we know that it has to go all the way to the end. Then the pole at minus 2. The pole at minus 2, it's a first order term. Its brake frequency is 2 radians per second. So nothing happens to it at 0.1, nothing happens to it at 1, but at 2 radians per second it brakes at minus 20 because it's a first order pole term. So minus 20, and it continues all the way. The last term is at the 0 at minus 3. Now if you have a look here, the zeros, they have a positive brake. So what is the brake frequency? 3 radians per second. What term is it? Is it a first order or a second order term? It's a first order term. So now if you have a look here, you'll see that nothing happens to it at 0,1, nothing happens to it at 1, nothing happens to it at 2, but at 3 radians per second it brakes at plus 20 decibels per decade. Now we go on, we calculate the total function here. So what is the total function? So at 0.1 radians per second, if you calculate the total, it gives you minus 20. At 1 radians per second, it gives you minus 40. At 2 radians per second, it gives you minus 60. And at 3 radians per second, it gives you minus 40. So this is how you do the magnitude slope contribution for a system. So this is your step 3. So this is where we are now. That is the step 3 that we've done. Okay. So based on this work that we did, let's do a assessment problem. Let's do one of the assignments assessments that we did previously. I think this was a problem that we did. That was g of s is equal to k into s plus 4 divided by s into s plus 2 into s squared plus 5s plus 25. So what we need to do here is 1, normalize, 2, create the description. We have already done these 2 parts if you look back into the work that you've done. But now the third one is creating the magnitude slope contribution. So that is the new part that we've done. So let's try and do this, and let's have a discussion about this. In our next class, we'll look at what we're going to do for the face slope contribution for the same portion. Okay, so thank you.